Stripping down science. The Naked Scientists.
Why don't women go bald?
Why does meat change colour when you cook it?
And can plastic water bottles affect your fertility?
Well, this show is sure pregnant with all of the answers. Hello, it is Sunday the 21st of October. It's our science question and answer special with me, Chris Smith, and also with Ginny Smith.
And this week, a potential new vaccine for the herpes virus that causes cold sores. And we're also joined by special guest Matt Parker, the stand-up mathematician. Hi there, Matt.
Hey, guys.
He'll be pitting his wits against your questions on anything maths.
Email chris@thenakedscientist.com or tweet @nakedscientists.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
Let's kick off. Ginny, this one's for you. And Elias Haddad says, why does red meat turn white when you cook it? In other words, why does meat change colour with heating in the pan?
Well, that's a really interesting question. So when you think about meat, it's made of protein. And when protein is heated, the shape of it changes. So normally it's quite a long molecule. But as it's heated, it actually shrinks. So if you imagine cooking a chicken breast, you see that as it cooks, it gets smaller. And it also changes colour. And this is because of the change in the proteins. And we say they denature. And that's when they go all white and they scrunch up and shrink. Red meat contains an iron-rich chemical called myoglobin, which also changes its shape when it cooks and changes colour from red when it's raw to a sort of brownish grey when it's fully cooked. Now, if you're cooking red meat, sometimes you get a lovely brown colour on the outside and that really tasty meat smell that always makes you hungry. And this happens because of something called the Maillard reaction. Now, this is a chemical reaction between the amino acids found in the protein and some sugars, and it requires heat to occur. So the temperature has to get up to about 154 degrees for the Maillard reaction to occur. And obviously this is higher than the boiling point of water. So that means that if there's too much water in your meat, or if your pan isn't hot enough, this browning won't occur. Your meat instead will cook in the water and it will just turn the light brownish grey colour without you getting any of that lovely crispy brown outside.
Certainly tastes nice, that's for sure.
Definitely.
OK, Ginny, thank you very much. Now, as we hinted at the beginning, also with us this week is Matt Parker. He is the self-styled stand-up mathematician. He's currently on a tour, which is promoting a light-hearted view of science and maths as part of the Festival of the Spoken Nerd. Hello, Matt.
Hey, Chris, how's it going?
Good, thanks. So you should be saying good day, I think, shouldn't you? Tell us a little bit about you, first of all.
As you've mentioned, I sit in the middle of a very weird Venn diagram. I work doing proper maths communication, so I'm based at Queen Mary University of London in the maths department, but I also work doing stand-up comedy, and so this tour is the combination of both those things. We get to do maths live on stage for comedy audiences.
The two wouldn't normally be regarded as good bedfellows.
No, and we're very excited that we actually get to take this on a tour because we started just doing a monthly night in London where there's three of us, myself, another stand-ups called Steve Mould and Helen Arney, and we began just doing the really nerdy comedy and experiments and music that we enjoy, and people started to show up to watch it, and we gradually got bigger and bigger audiences, and we started selling out bigger venues, and now we've been taken on a 22-date tour all across the UK.
For the first time?
Yeah, this is it. This is our first ever tour. We're going out bringing live nerdery to the people.
Who comes along and listens to maths comedy?
Well, we try and be very inclusive. So we do obviously attract a wide spread with some extreme values of nerds. So hardcore nerds show up, and believe me, there is something in there for them. But they tend to also bring friends and partners and members of their family who aren't as nerdy. And so we've worked very hard to make sure that this is also a legitimate comedy show. So you can come, you can enjoy the show without having got, a very good A-level in maths.
Or even a very bad A-level. How do you actually make maths funny? So tell us a bit about the content of the show. What sorts of things do you discuss?
So we try and, in this show, do all the sciences. A little bit of physics. So we've got a flame tube, which is this amazing kind of flame graphics equalizers, and we can put different frequencies into it, and it responds different ways. I will be solving a Rubik's Cube live on stage. I'll also be doing a very dangerous experiment. I'm recreating one of Michael Faraday's experiments from the Royal Institution, where I'm using parabolas to set things on fire. So it's just all our favourite nerdy things that we can do on stage, occasionally involving fire.
So how do you come to be here doing this? Because you're originally from Australia, aren't you? Western Australia.
Yes, I do strange things to vowels. I'm from Perth originally, where I studied and went to university at the University of Western Australia. And I did physics and then went in and did maths. And after that, I became a secondary school maths teacher. And so I moved to London about 8 years ago to teach maths. And I've gradually shifted from being a normal, I've used the word normal carefully, maths teacher in schools, into working part-time for university and also doing comedy part-time.
It's quite brave of Queen Mary University of London to say, well, let's actually make a job around this sort of thing.
Queen Mary have been incredibly supportive. So I'm their public engagement in maths fellow, and so a lot of my job is to communicate maths to other people. So I do a lot of maths writing and things like this, lots of maths media. But I also work with the academics and the students, and so a decent amount of my job is training and working with the undergraduates to help them communicate maths to other people and to go into schools and work with young people. I also work with the academics to help them communicate the research they're doing to other people who may not know as much maths.
Do you actually have any evidence as to whether this translates into a tangible benefit, a measurable benefit for QMUL? In other words, do you see lots more people applying into maths as undergraduates than you would have done were you not there?
Well, Queen Mary do keep a close eye on where people apply from, and they can try and find out how they heard about it, but that's much harder to get to. So we do track numbers of people applying, and we do track where they live when they apply to the university. But all the work that I do is not focused just on getting people to come to Queen Mary, although I'm biased. I think it's a great maths department. My goal, and in fact all the outreach work we do at Queen Mary, is to get people excited to do maths or something sciencey related, but we don't mind which university they go to. We just want more young people going into the science subjects.
Right, well, we're going to put you to the test because, as we said at the beginning, you made this fairly grandiose claim that you could work out the numbers in barcodes for people. So we have invited people to start calling in with barcodes. We have two lined up already. Tilly also has a question for you, and she's with us now. Hello, Tilly.
Hello.
Right, fire away.
My question is, an aeroplane carrying out a parcel drop releases a parcel while travelling at a speed of 90 metres per second at an altitude of 200 metres. Calculate the time taken between the parcel leaving the aeroplane and striking the ground, and also the horizontal distance travelled by the parcel in this time.
Tilly, are we answering your maths homework for you by any chance?
No, it's physics.
Physics homework, it is homework.
Yeah.
Okay, Matt, what do you think of this one? Can you do Tilly's homework for her?
You wouldn't be doing the equations of motion for projectiles, would you, Tilly?
Yeah, it is.
Right, so how fast is that package going to fall as you release it?
I don't know.
See, this is the teacher in me. I try and talk the student through the question.
Yeah.
Well, I guess initially, it doesn't matter how fast you're going forward. If you let go of this package, it's not going down at all. Well, yet, because gravity will kick in. And so initially, it's going to start at 0. So if you put down your starting velocity as 0, it's then going to accelerate according to gravity, which is about 9.81 meters per second squared, I think.
Yeah.
And so now, do you know which equation you have to use to work out how long it's going to take to hit the ground?
So maybe SC equals UT plus half AT squared?
Oh, no, UT plus a half AT squared. What's the other one? Was it V squared equals U squared plus 2AS?
Yeah.
It's amazing. These things just get locked in your muscle memory.
Yeah.
So, right, what you want to do now is write down, I feel like I'm just doing tutoring live on the air. This is great for you and me, Tilly, but everyone else is getting a bit bored. You need to write down everything you know. So you know your starting velocity, you know your acceleration, you know the distance it has to travel, and you want to find out the time.
Yeah.
And so which of these equations has U and S and A and T in it? So now if you put all your numbers into that equation, in theory, so it's going to be 200 squared equals 0 times time plus a half AT squared, and acceleration is about 10, so that's 5, 4, 0, 0, 0, 0. Okay, so it's around about, divide that by 5, 8, square root of 8,000 seconds. So
that's the time to hit the ground, isn't it, for the parcel, Matt, from that altitude? So now we've actually got to take into account the movement of the aeroplane along.
So I'm going to cheat and use a calculator at this point to work out what that would be. Now, all you need to do then is, if you know how fast your plane's going, do you say 90 metres per second?
Yeah, 90 meters.
See, you multiply, while the parcel's falling, multiply how long it takes to hit the ground by 90, because it's going to go an extra 90 metres every second, and that will give you your grand total, which will be around about... Where's my square root button? Okay, so it's going to take about 90 seconds-ish to hit the ground, which means the plane will go approximately 8 kilometres.
Okay.
Oh, there you go. That's not bad.
There you go, Tilly. So if you get an A, we want some of the glory, okay?
Yeah.
All right, you've got a barcode for Matt, so let's
Yes.
try this out. So, Matt, let's do the barcode trick that you're saying. You can tell
Yep,
Tilly what her last digit of her barcode is?
Have you got the product there, Tilly?
Yes, I have.
What is it on?
I think it's coffee.
Oh, I think it's coffee. You should have had the coffee, and then you could have done your maths homework a lot easier. That's my professional advice. But okay, if you see the barcode, and in fact anyone else can play along,
Yeah.
can you see all the digits are underneath some vertical lines?
Yep.
Do they start just to the left of the lines or directly underneath?
Start just to the left.
Okay, cool. Okay, I'm going to get you to read those digits out very slowly. I'll
Yep.
say yep after each one.
Okay.
Don't tell me the last digit. I'm going to try and calculate it in my head.
Okay.
If I get it right, can you shout yes in a very excited fashion?
Okay.
Okay, here we go. What could possibly go wrong?
8,
Yep,
7,
yep,
1,
yep,
1,
yep,
0,
yep,
0,
yep,
0,
yep,
3,
yep,
0,
yep,
2,
yep,
5,
yep.
and 9. And then there's the last one.
Ooh, is it a 0?
Yes.
Well done, Matt. Tilly, thank you for joining us.
Thank you.
Katrina's with us. Hello, Katrina. What can we do for you?
All right, well, my elderly mother has a hand that feels warm to the touch, but to her it feels freezing all the time, especially the fingertips. And it's so cold it hurts. Now, she can't get her GP to take this seriously, especially as she recently broke her other arm. So they're concerned about that one. Now, any idea what this might be? You know, I was wondering if it might be a form of neuropathy. And then is there anything I can tell her that she can tell her doctor? And can anything be done for it?
It sounds quite likely, actually, Katrina, that this is a form of neuropathy. The sensation of pain and temperature in the body is conveyed by what we call C and A delta nerve fibres. They're some of the tiniest nerve fibres in the body. They measure less than 1 micron or 1,000th of a millimetre across. And for some reason that we don't thoroughly understand, if you injure them or injure a nerve, or you have certain conditions like diabetes, or you take certain drugs to treat other conditions, this can sometimes damage these nerve fibres. And when they are injured, they don't regrow or regenerate very well. And as a result, what can happen is that you can get a condition called causalgia, or another related condition called allodynia. And this is where patches of skin which are supplied by these sensory fibres can become excruciatingly painful when the stimulus applied to them is one that would be completely innocuous normally. In other words, a stroking sensation can be misinterpreted as an extremely painful sensation. This can occur secondarily to an injury. If people break their wrist, for example, especially elderly people, and they fall over, they can sometimes damage the nerves in their wrist, and this can result in damage to those sensory nerve fibres and can produce these similar sorts of sensations under certain circumstances. Unfortunately, it's very hard to treat. There are some drugs that can be used, and these include amitriptyline in very low doses. This is an antidepressant in high doses, but at low doses can be good for these sorts of neuropathic pains. And other drugs like gabapentin also does the same sort of thing, and it might be worth seeing a neurologist to see if they can help her. It's also worth getting this checked out properly anyway, just in case there's anything else going on that we might be missing, some other related signs that might point towards another disease that might be causing this. But I hope you can get us sorted out soon. I understand, Katrina, you also have a barcode for us.
Yes, I do have a barcode for you. Okay, 0,
Yep.
1,
Yep.
7,
Yep.
2, 2,
Yep.
9,
Yep.
1,
Yep.
3, 8,
5.
Four.
Yep.
and then 3,
Yep.
And that's it until the last one.
Ooh, I'm not sure if that is a standard UK barcode. I think the last digit is a 4, but I'm only about 50% confident that that's correct.
Is that right?
I bought this in America.
Aha!
There you go.
Right. I knew there was something up with that barcode.
The Americans are chucking a
That's
spanner
actually
in the
quite
works.
interesting because they use a different pattern in their barcodes, and so that my sum wasn't working in my head. So thank you for putting me out of my misery. I was getting worried there.
There you go. Simon is in Norwich. Hello, Simon.
Hello there.
Fire away.
Does vegetable matter have any measurable intelligence or ways of measuring its intelligence?
I'm going to ask Ginny, who's our psychologist, what she thinks about vegetable intelligence.
That's an interesting question. So I guess it depends how you define intelligence. In the way of sort of problem solving and flexibility, thinking, that sort of thing, I would say probably not really. But there are things that plants can do that seem intelligent. So there are types of creeper that manage to grab hold of other plants and climb up them and use them for support. And that seems quite clever. And I've seen time-lapse videos of those where you can see the creepers sort of spiralling round and reaching for something to hold on to. There's also the fact that when you plant a seed, the roots always know to grow downwards and the shoots know to grow upwards. And that's because of some chemicals that are in the plant that tell it which way gravity is, and that allows it to know which way up to grow. So you don't have to worry about which way up you're planting your seed. So there are things plants can do that do seem quite clever and quite intelligent. So, yeah.
Do you have any intelligent vegetables in your garden to tell us about, Simon?
Well, I was thinking about a Venus flytrap.
Of course. Well, Venus flytraps are very clever. They've got actually hairs on the inside of the trap part. And what's particularly clever about them is that they don't get triggered if just one hair is touched. And that's to save energy because it's quite energetically expensive for them to close. And if they did it every time a leaf fell on them or a drop of rain or something, that would be a waste. So they only trigger if 2 of the hairs are brushed in quick succession, because that's quite a good indicator that there's something moving on the inside and it's a good idea to close and trap it.
So I guess it is a sort of intelligence because they're summating or mixing together 2 different signals from 2 different hairs to work out when to do that behaviour. So I guess that's a reasonable example, Simon.
Okay, that's cool.
Well, I mean, you know, of course, why they do that.
Because it's very poor nutrition in the ground.
Yeah, I mean, these plants are said to acquire their nutrition from the air, meaning that their lunch delivers itself part and parcel straight onto their leaves. And as you say, these sorts of plants grow in areas where the soil is extremely poor, often bogs and marshes, where they can't compete very easily for nutrients from the water and the soil. So as a result, they actually trap things from the air which are rich in nitrogen and phosphorus, i.e. living matter, and they ingest it into themselves and make it part of themselves. Great question. Now, you're listening to The Naked Scientist with Chris Smith and with Ginny Smith, and also with Matt Parker, the stand-up mathematician. We're answering your science questions this week. More of those in just a second, but first let's take a look at an important news story that's broken this week, in which scientists say that they have come up with a vaccine against herpes simplex virus, the cause of cold sores and genital herpes. It's very difficult to prevent this virus from gaining access to our body. And once it's got in, it then hides in the nervous system. It goes what's called latent, and it just exists as a tiny piece of DNA inside your nerve cells. And then periodically, the DNA activates various genes and it reassembles new virus particles inside the nerve cell, sends them out to the patch of skin that was first infected, and it produces a new lesion there, a cold sore or a genital ulcer, which is infectious, and you can then pass the infection on to other people. Now, people have tried to make vaccines to stop this, but the problem is that they found that although you can make the immune system respond to a vaccine, it's really difficult to get enough immune responses at the sites where the virus tries to get in. In other words, through skin surfaces, the mucous membranes of the mouth or the genital tract. So what a group of researchers at Yale University in the States have published in the journal Nature this week, this is Heina Shin and Akiko Iwasaki, they've come up with a whole new strategy for vaccination that they call prime and pull. And what they do is they administer to a mouse a type of herpes simplex which is an attenuated virus. It's a weakened form of the virus, which they put into the skin somewhere. They then wait 5 days, and then they introduce to the vagina two chemicals called CXCL9 and CXCL10. These are completely natural signals made by the immune system to attract immune cells to certain tissues that need an immune response. And so by putting them into the animal's vagina, what you end up with is the immune system being attracted to that site. And when they look in these mice, they find very high numbers of these so-called CD8 cytotoxic T cells that fight off virus infections, including herpes simplex. Now, to test whether this would actually protect the animals, they then challenged them, including up to 3 months after the vaccine strategy, with what would normally be a lethal dose of herpes simplex. And what they found is that all of the animals that had been vaccinated survived, and only about half of the control animals that had just had the vaccine into the skin survived. When they looked in the nervous systems of these animals, which is the critical thing to see if you're going to stop this virus invading the nervous system from which it can keep reactivating during life, they found that the animals that had been treated with the new prime and pull technique had orders of magnitude less virus in their nervous system compared with the control animals.
Oh, that sounds like a great finding. Do you think this has applications in humans?
It could do. I can think of a few problems with it. One of those problems being that 80% of us are already infected with herpes simplex, the cold sore form of the virus. And that means that it's already in our nervous systems. So this sort of thing is not going to help. So we'd have to get in early. So in other words, that means probably before the age of 3, because most people pick up herpes when they're a toddler and they get it from their parents when they kiss them. So you've got to go in early. So for most of us who are probably already infected, unfortunately, it's too late. But there is some other tantalising information hidden in this paper in Nature, because what they say is that, and I'll quote, a single topical treatment with the chemokines, that's the CXCL9 and 10 signals they put in, applied vaginally can provide superior protection against genital herpes by preventing the spread of the infection from the mucosa into neurons. And then they go on to say, maybe the same strategy could work with HIV, because you could use the same prime and pull technique to get anti-HIV immune cells into the genital tract, so that when HIV tries to get in, they're already there, ready and waiting to knock it on the head before it can infect the kinds of immune cells it's trying to target. So there could actually be a 2 for the price of 1 in here. An amazing piece of work.
Yeah, that really is amazing.
You're listening to The Naked Scientists with Chris Smith, with Ginny Smith and with Matt Parker. Matt, we've got this one in for you.
Hi there, it's Andy Spriggs here, and the Spriggs family have a question for The Naked Scientists. I introduced my sons, Peter and Jonna, to the concept of a Googol several years ago. For those who don't know, a Googol is 10 to the power 100, or a 1 followed by 100 zeros. I also told them that I didn't think there was a Google of anything in the universe. Since then, Peter and Jonna have been trying to find something. They started with the grains of sand in the Sahara Desert. Nowhere near, about 10 to the power 28, I reckon. Eventually, we got to the number of photons in the universe. My rather rusty maths and physics got that to 10 to the power 87, which leaves it 10 trillion times smaller than a Googol. But I've never been able to prove this. It would be good if the Naked Scientists could oblige. And could you get us past a Googol of something, anything? Thanks, guys.
Matt.
Yes, so a Googol is a great number in that it is a number that exists just because it has a nice name. Like he said, there's nothing that we really have there's a Googol of, but someone thought, well, wouldn't a 1 with 100 zeros be a great number? So they called it a Googol, and you could hear him emphasizing Googol because it's spelt Googol. And in fact, Google search engine is named after this, but they spelt it differently. So they spelt it with an LE instead of an OL. He's absolutely correct. If you're going to try and count objects, you won't find a Googol of anything. So even going right up to number of protons in the universe, which I think is, physicists argue between 10 to the 79 to 10 to the 81. So it's a 1 with somewhere between 79 and 81 zeros. But I have found one thing which we have more than a Googol of in the universe.
Well, should we ask Ginny if she can guess what it is?
I don't know. I mean, I was thinking about neurons because they make an awful lot of connections, but I think when we were thinking about this, it probably wouldn't be quite that many, even if you include all the animals on the Earth.
10 to the 11 nerve cells in a brain, 1,000 connections per nerve cell brain, so they're probably about 10 to the 14, so we're still a long way short of Matt's Googol.
Yeah.
Yeah, actually, you're not far off from what I decided on. Because when you're talking about connections, well, suddenly you're looking at different ways of combining things. And so I looked at how many ways you can shuffle a pack of cards. So if you got a pack of 52 cards and you shuffle it, you can work out there's about 10 to the 67. It's 8 times 10 to the 67 ways to shuffle a pack of cards, which is a lot more than the number of grains of sand in the Sahara, which here worked out. In fact, if you got a pack of cards with just 27 cards, you would have about 10 to the 28 different ways to shuffle them. If you want a Googol, if you get a pack of cards with 70 cards, so you're going to need your normal pack and then get 18 from a pack, maybe with a different colour on the front or the back so you can tell them apart. If you shuffle 70 cards, there's a Googol of possible ways to arrange them.
Beautiful. I was thinking of a similar example, Matt, because I was looking at the power of passwords on the internet. Someone was asking a question on our forum, nakedscientist.com/forum, and they were discussing the power of encryption and saying if I took a brute force attempt to crack a password just by taking random choices, how many possible combinations of a password encrypted with a certain number of bits of encryption, and you end up with something which would take trillions of centuries to solve, and the number of solutions, I think, is way more than a Googol.
Yeah, again, you're looking at number of possible combinations. So, in fact, a password's pretty close to a pack of cards because you've got the alphabet, upper and lowercase, and then you do actually get extra symbols and bits and pieces. So if you've got a password of even just, 8 characters, you're already up into the very high tens of thousands. And much bigger than that, you're into millions, billions, and well off very quickly.
Thanks, Matt. Alan in Milton Keynes. Hello, Alan.
Hello there, Chris. How are we going?
Good, thank you. What can we do for you?
Quite often I go out in the morning, and I'm in Milton Keynes, so I would expect the moon to rise in the east and set in the west. Sometimes I've got 2, 3, 4 o'clock in the morning, and the moon is low in the east. Wondering how that worked out.
Oh, I see. OK. Well, let's just sort of zoom out for a bit and imagine you're off of the Earth and you're looking at the Earth and the moon from space. Mm-hmm. So you have the Earth is the bigger of the two bodies sitting, let's say, in the centre. Yep. And the moon is in orbit around the Earth. Are you with me so far?
Yep.
So the moon goes round the Earth, and the moon takes a month to do a complete lap of the Earth and get back to where it started. 28 days to do a complete orbit of Earth. With me again?
Yep.
Yep. Also, inside the moon's orbit, the Earth is turning, of course.
Yep.
And the Earth takes 24 hours to do a complete circle.
Mm-hmm.
So, therefore, as the Earth turns, then it's going to see the moon from one side of the Earth go across the sky and then down on the other side. So you're going to see the moon rise and set.
Yep.
But because the moon is also doing a lap around the Earth, the moon is going to appear at different points in the sky at different times of the day and night. So sometimes the moon will be up during the day.
Yeah, that's why you see the sun and moon at the same time.
Exactly. And so it's all to do with where we are in that so-called lunar cycle,
right.
Which takes 28 days.
That's cured that one for me.
No problem. Have you got a barcode, I understand you have?
Yes.
Let's put Matt to the test. Is this an English product this time? So no tricksters.
I bought it in England.
OK, so Matt wants all of the numbers apart from the very last one. You ready, Matt?
I'm ready.
OK, your credibility is at stake here because the last one caught you out with an American
I know, I'm 1
barcode.
for 2 at the moment.
Fire away.
It starts with one number left of the barcode. 5.
5, yep.
3.
Yep.
9.
Yep.
0.
Yep.
0.
Yep.
0.
Yep.
3.
Yep.
0.
Yep.
0.
Yep.
8.
Yep.
2.
Yep.
1.
The last digit is a 5.
Correct.
We'll tell you how he's doing it later in the programme. Thank you also. Mark Wilson is wondering, he says, are humans the only picky eaters? Or are other animals fussy too?
Well, there are animals who are very fussy. For example, pandas only live off bamboo, so they'll only eat that one thing. But I think what he was really asking is whether there are animals like humans where certain individuals do and don't like particular foods. When I looked into this, I found many more reports of this in pet animals than in wild animals. So there are lots of people out there who report cats who'll only eat one brand of cat food and dogs who leave certain bits of their kibble. So I was thinking it may be that it may be that we just notice it more in pets than in wild animals because we spend more time with them. Or it may be something that only happens when food is plentiful. So you can imagine that even a child who hates broccoli, if it was the only thing available for them to eat, they'd probably eat it. So it could be that picky eaters only really exist when there's plenty of food around.
Anything you're particularly fussy about?
I'm not a big fan of mushrooms. I find them a bit slimy, but generally I eat most things. There was one other thing I found about this, though, that did seem quite interesting, was that they found that some predators tend to choose their food on the basis of nutritional value rather than just calorific content. So when food is plentiful, they'll tend to choose the right diet to maximise their chances of reproducing, so the right proportions of fats and proteins and that sort of thing. So it could be that sometimes being picky is actually for the best for your genes in the long run.
Do mathematicians have any dietary foibles?
I can't stand porridge.
We're getting people sending you suggestions of jokes for your act now, Matt.
Oh, really? Oh,
Maths
good.
in
I'll
the City.
crowdsource this.
Maths in the City says on Twitter, what did the number 0 say to the number 8?
Oh, this is a classic. Nice belt.
Yeah, where did you get it is the only thing I can add to that one. And Simon in Norwich contributed at the end of his question. He was the guy asking you about vegetables and intelligence and things. He says, what's a mathematician's favourite food?
Oh, what's the mathematician's favourite food? Would it be chips because they're square root vegetables?
Oh, that's poor.
That's the best I can do at short notice, all right?
No, he said pie.
Oh, yeah, pie.
Barbara is on the line. Hello, Barbara.
Hello, Chris.
Fire away.
Well, I was wondering why bleach, you put it on certain things and the colour disappears, and yet I can put it on my draining board and nothing happens. So where does the colour actually go?
Oh, I see. So how does bleach stuff? Well, many bleaches, bleach is a fairly common word which is used to describe a range of different things. Some forms of bleach, and the household bleach that you put down the loo and stuff, has usually got a lot of chlorine in it. In fact, the active chemical is a substance called sodium hypochlorite. It's the same stuff that they put in swimming pools. Other forms of bleach include hydrogen peroxide, the stuff that you bleach your hair with, and you can also use for mouthwash and teeth whitening and, say, sterilising your contact lenses, for example. But they're called bleaches because they can react with things to take the colour out of them, like hair. Now, the way it works is that these molecules are reactive. They're oxidising agents. And things that have colour are usually big, chunky molecules that have lots of electrons going around the molecule. And when light comes in, the light waves, which are little packets called photons, interact with the electrons in substances, and certain colours of light will be preferentially absorbed by those electrons, whilst other colours will be reflected. So when you see something and it looks, say, red, the reason it looks red is because all of the light hitting it is being absorbed by the molecules, except the red colours, which are being reflected back to you. When you mix a certain chemical with these oxidising agents like hypochlorite or contact lens solution, hydrogen peroxide, the oxidising effect breaks open the molecule, damaging it or affecting its structure in some way, so that the electron cloud, which was doing that absorbing, now changes its shape. And that has the effect of stopping the chemical from absorbing certain colours. So instead of it, say it goes white, instead of it absorbing certain colours and not others, now it reflects everything back at you. And when you mix all the different colours together, you see white. So basically you're changing the chemical structure of the thing that was giving the substance its colour in the first place.
Oh, that's very interesting. Very interesting.
So now you know how to do it. Do you have a barcode for us?
Well, my husband's written it down, but it's rather a long one. I wonder if he's done it right. This is a reduced item, by the way, but...
What is it?
It was a sandwich, actually. I've just got an empty sandwich pack.
Right, okay, let's see.
Actually, I'm gonna save you reading out the rest, because the pattern they put into reduced items is different to the pattern in the original commercial barcode. Because the reduced item barcode contains more information. So if it for example, if this is from Tesco's, and I think Sainsbury's as well, you can actually see the reduced price hidden in the barcode if you look at the digits very closely.
Yes.
And so, because they have to put in more information, they use a different pattern. But what some people have suggested is that if you learnt the new pattern for reduced barcodes, you could go around and sneakily change the digits. But I obviously don't support any of that kind of behaviour.
Ooh. So what would you have to do to the numbers then, Matt?
Well, what you need to do, first of all, is keep the ones that tell you what the product is the same. Then you want to change the ones that tell the checkout what the price is. You want to change those. But then you have to recalculate the other digits around them. So I'm doing a calculation in my head to make sure all the digits match what they should be according to the pattern. And if you change some of them, you have to change the other ones to keep the overall pattern the same.
So are you going to be able to do this barcode, or does this not work because it's a reduced item?
I don't know, and it changes from supermarket to supermarket. I don't know what pattern is in this barcode, so I'm afraid I'm now 2 for 4. I can't do this one.
And you're going to have to pay. You're going to have to pay for the rest of your sandwiches in full rate in future, Barbara, I'm afraid. Thanks, Matt. Ginny.
Headlines like "palm trees grew on Antarctica" abounded when climate scientists recently found evidence that the southernmost continent was once a very different world to the one we know now. The research was reported in the journal Nature and is part of an international project to examine the Earth's climate during the Eocene period between 34 and 56 million years ago. This is because by looking back into the past, they are examining the potential future of climate change. Planet Earth podcast presenter Sue Nelson met up with one of the paper's authors, Dr. James Bendel from the University of Glasgow, in a suitably balmy location.
We're in the Royal Botanic Gardens in Glasgow, and we are in an area where there's tree ferns and we're surrounded by palm trees. It's probably 22, 23 or so degrees centigrade, and it's very humid and very warm.
It's extremely warm and sticky, and about probably as far from Antarctica as you would think.
Yes, but if you went back in time 50 million years or so to the edge of the Antarctic, you'd look out on an array of vegetation that would look very much like this, and you'd probably be experiencing very similar temperatures.
How do you know this?
I took part in an expedition 2 years ago, an ocean drilling program expedition to the margin of the Antarctic, an area called Wilkesland. We drilled down through 4 kilometres of water and 1 kilometre of sediment, and then recovered rocks and sediments from a period called the early Eocene 50 million years ago. And it's a period of time that is being studied by climatologists as an analogue for where we might be going in the future. It was what we call a greenhouse world. There was very high levels of CO2 at that time. We didn't know much about the Antarctic until that expedition. Some of the results that we've found, some of the headline results that we're now publishing, show that there was an incredible subtropical assemblage of vegetation on the margin of the Antarctic.
And was this known before?
No, not from the East Antarctic. The interesting thing is that we've recovered pollen, and that's work that's been led by our colleagues in Germany and Frankfurt. And at Glasgow, working together with colleagues in the Netherlands, we've been looking at these molecular fossils, organic compounds that are preserved in the same sediments. The vegetation assemblage tells us that it was this subtropical world. We also recovered these pollen of plants called Bombaceae, which are very characteristic rainforest trees with a huge sort of splayed trunks at the bottom.
How long did this tropical period of Antarctica last?
Well, we only see the really warmth-loving species like the palm trees and the Bombaceae on the Antarctic coastline during the peak warmth of the early Eocene. Within a few million years, they disappear and they get replaced by Northofagus, which is southern beech tree, more like the kind of temperate vegetation you might see in New Zealand. This was existing in the mountains, but it came down and took over the coastlines as the climate was cooling. The climate was cooling at that time because Tasmania and Australia break away from the Antarctic. We get the opening up of an ocean gateway and a new cold ocean current surrounding the Antarctic, and the climate starts to cool.
And then it heads towards millions of years later, more like the Antarctic that we know today.
Yeah, then by 34 million years before present, we see another really fast stepwise cooling, and the continent glaciates and it loses its vegetation.
Now that you know then what Antarctica was like all that time ago, and at a time when its carbon dioxide levels were high or similar to what they are now, are you effectively seeing the future of Antarctica like that again?
If we reached CO2 emissions that were similar to that time and we let the climate system and the vegetation in Antarctica get to equilibrium, then yes, eventually. It might take several thousand years or so, but yes, that is the direction that we will travel in if we continue with unabated emissions.
When you were doing this research, when it was probably cold, icy, could you envisage that you would uncover a world that's actually far more like this stuffy, steamy, tropical plant house that we're in now?
A couple of times we had to move away from the area the ship was drilling in because we'd had quite large icebergs that had been coming too close to the ship. So we were in that, Southern Ocean, big ocean swells, grey skies, really cold, icebergs around. And then when you're drilling through these geological sediments, you are effectively becoming a time traveller. And it is amazing now that we have the data after several years of work to look at that data and to imagine this world where it never got below about 10 degrees centigrade in the winter. It was at least as warm as 20 degrees in the summer, maybe warmer. And then really, I think aesthetically, it's the vegetation assemblages, knowing that there was palm trees and these Bombaceae trees and tree ferns is just an amazing thing to think about.
Dr. James Bendel from the University of Glasgow, and a potential warning to what might happen again to Antarctica if CO2 levels continue to rise in the future. That report, along with other news from the natural world, can be heard on the Planet Earth podcast. Follow the links from our website or via Planet Earth online.
It's The Naked Scientist, Chris Smith and Ginny Smith, answering all of your science questions. Ginny, quick one for you. Why don't women go bald, wonders Janet France.
OK, well, women can go bald is the first thing I should say. There are various illnesses. One's called alopecia universalis, which is thought to be an autoimmune disease which attacks the hair follicles and can cause you to lose all your hair, including eyelashes, eyebrows, everything. And that affects both men and women. But if we're talking about male pattern baldness, which affects up to 80% of Caucasian men by the time they're 70, so a lot of men, you're right, it doesn't affect women quite the same way. And this is because it's caused by a male hormone. Now, it's highly genetic and can be inherited from either parent, contrary to popular belief, but it's caused when you have high amounts of dihydrotestosterone, which is a derivative of testosterone, which, as we all know, is in much higher concentrations in men than in women. And this causes the hair follicles to atrophy. They actually sort of shrivel up. And the hair produced then becomes progressively smaller and thinner and finer until it's practically invisible, or it may even disappear completely. Now, hormones do also play a role in women, so sometimes people experience hair loss during pregnancy, menopause, any time when hormone levels may vary. But as I say, it's mainly testosterone that's the culprit, so that's why it affects men much more than women.
Thank you very much, Ginny. Matt, on Facebook, Ravi Nair says, when will we find out if pi is normal?
That is a very good question, because at the moment we don't know whether or not pi is normal. And normal has a very specific definition in maths. So if we say a number is normal, it means that any string of digits is equally likely to appear in its decimal expansion. And so the decimal places of pi go on forever and they never repeat. But we don't know effectively how well distributed they are if you go far enough down. And we've checked trillions and trillions of digits, and it's been normal all the way so far, but we can't guarantee that it will continue to be normal after that. And so I suspect it's going to be a while, because we currently don't have any really good mathematical techniques to explore that far into pi, or to find some way to pin down to show why it is or isn't normal. But hopefully one day people will develop some new mathematical ideas and we'll be able to answer that question.
I was watching Star Trek the other day, as you do in the evening, The Next Generation, and I was watching a Jean-Luc Picard. You well, all right, calm down. I was watching Jean-Luc Picard, otherwise known as Patrick Stewart, and he was struggling with a difficult maths problem, and it was Fermat's last theorem, and I thought, they're all walking around on Star Trek with what we now call an iPad. They've got doors that open automatically with a whooshing noise, otherwise seen at the average supermarket, and they were still struggling in the year 2000, whatever it was, with Fermat's last theorem, which was famously solved far more recently, wasn't it?
Yes, a mathematician called Andrew Wiles solved it about 1994, but it was originally posed in the year 1630 by a guy called Fermat, obviously, and it took mathematicians well over 300 years of constantly developing new bits of maths to be able to solve it. So you can see why, even before the 90s, when it still looked incredibly unlikely, that people think, well, maybe it is another couple hundred years. Well, it turns out we had it down by 1994.
Now, I've got a question here from Rosemary, who says, is there a possibility of infertility from drinking water out of used plastic bottles? Now, this is an interesting and emerging area, because the question that everyone is beginning to consider, I was going to say the question on everyone's lips, but that's a bit too bad a pun for drinking bottles. But the thing is that it's becoming clear that the bottles and the plastics that we use in our everyday lives contain chemicals which we now regard as endocrine disruptors. These are chemicals that can mimic the behaviour of certain hormones in the body, especially female hormones. And one of these chemicals is called bisphenol A, and there are also chemicals leaking out of other types of plastic which get into the contents. Now, I did read one paper which was published a couple of years ago by a guy called Martin Wagner, who's a researcher at the University of Frankfurt in Germany on this subject. And what he and his team did was to go to their supermarket and they bought a very large cluster of plastic bottles containing mineral water. And this wasn't mineral water that had been made artificially. This really was mineral water out of the ground. They emptied all of the water out of the bottles, and they refilled the bottles, and they also took a second group of glass bottles and filled both with laboratory-grade water, which they knew was pure. They put into the bottles some snails. They're in fact snails called New Zealand mud snails. And they kept them in the bottles, feeding them in ideal circumstances for a couple of months, and they then totted up the reproductive rate of the snails. The animals kept in the glass bottles had half as many embryos as the animals that were kept in the plastic bottles, and it was a statistically significant result. And so Martin Wagner's interpretation is that there is something leaking out of the bottle which is getting into the water, which is acting as an estrogenic-like chemical in these snails and making them more reproductively active. And therefore, the extension to that is that if we're using the same products, we're almost certainly exposing ourselves. But obviously, we're not a snail, so you've got to interpret it slightly cautiously. But at the same time, returning to Rosemary's question, if you reuse a plastic bottle, is that a risk? Well, actually, you'd argue the more times you use a plastic bottle, the less risk there is, because by the time the plastic bottle's been used to the point where it falls apart, you've actually drunk all of the endocrine disruptors that were in it, so the concentration is getting lower and lower all the time. So it's getting less and less bad for you the more you use it. It's probably worse for you when you have a new one. Trevor is in Norwich. Hello, Trevor.
Hello there. Hello, Chris.
Hi, fire away.
When we talk about the lottery, we always refer to it as a 14 million to 1 chance of winning it. And I just wondered, if you based it on sort of doing the lottery, say, on a Wednesday and a Saturday, so that's two £1 stakes, and you started doing it when you were 20 years old and you lived till 80, I was wondering how that would equate in lifetimes. So if I went in work and I said, well, in actual fact, it's going to take you 100 lifetimes, that's the realistic chance of winning it. I don't know what the figure is, and I wondered what the figure would be.
Okay, well, let's see if we can work it out fairly quickly. So if you start playing when you're 16, let's say, and you cease playing when you're 86, is that reasonable to give us 70 years of non-stop playing?
70 years, yeah.
Okay, so it's about 100 games a year. So you'll end up doing about 7,000 games across your lifetime. So what you need to do is, if it's originally 1 in 14 million, we'll divide that by the 7,000 games you're going to play, because you'll have 7,000 chances to win, and you end up with 2,000. So you need to have 2,000 lifetimes to expect to win the lottery, yeah.
Yeah, that really is. That's more alarming, I think, than actually saying 14 million to 1. So I'll enjoy sounding that in work tomorrow. But the other, have I got time to give you the second part?
Yes, fire away. Go on.
I'm happy.
Yeah, the other second part is to do with the lottery again. If you do the numbers 1 to 6 in the lottery, I think your people who do that are being silly on the basis of the first 3 balls come out on the night, and it's saying number 1, number 2, number 3. The chances of 4 to 10 coming out next diminishes. Is that the case?
If you look at the lottery as a whole, like from before you start pulling out the balls in a particular draw, any list of numbers you pick is equally likely. So you can pick 1, 2, 3, 4, 5, 6. You could pick random like 12, 37, 14, or some random numbers. Every single string of numbers has exactly the same chance of coming out. What you're saying now is once you start drawing the balls out, how does the probability change? And what people often forget with things in probability, because as humans we love to assign meaning and pattern to things, is that if you draw out one number, it doesn't change the odds of the next number at all, other than you can't draw the previous number that just came out. There's now one fewer, or during the draw, fewer and fewer balls in there. So actually, your odds aren't going to change as you're drawing those numbers out as you go along.
Matt, thank you very much, and thank you also for an excellent question, Trevor. Now, Dally Wave Rider said on Second Life, by the way, the reason you don't want to use a pattern in the National Lottery is that you'll be more likely to have to share if you do win. Well, it depends how generous you're feeling, I suppose. Anyway, it's The Naked Scientist with Chris Smith, with Ginny Smith, and also Matt Parker. It's our science phone-in extravaganza. We're looking at all of your science questions this week. Lots of interesting things have come in, but lots of you were intrigued by how Matt was actually working out what numbers were in these barcodes. So, Matt, time to reveal all. How do you do it?
All right, I'm doing exactly the same calculation that the checkout does at the supermarket when you scan a product, because we deliberately put a pattern into the digits in barcodes. So what you need to do is, as the person's calling out the numbers, initially you need to remember and then add together every second digit. So ignore the first one, remember the second one, ignore the third one, add on the fourth one. And so you add every second digit together. You then get this total, you multiply that by 3, and then you add on the digits you skipped over. And the grand total in all UK product barcodes, if you add every second digit, multiply by 3, add on the other digits, is always a multiple of 10. And so if I do that calculation, I know the last digit is whatever's required to bring the total up to the nearest whole multiple of 10. So you may, if you're listening earlier, I sounded a bit uncertain when I predicted the last digit was a 0 on someone's barcode. And that's because I already had a multiple of 10 without the final digit. But thankfully it was a 0 because it didn't have to increase it. It's a bit tricky in your head to keep track of 2 different totals and to multiply one by 3 and add them together. It depends how much free time you're prepared to throw at learning it, I guess. I am a hoot at parties. But a lot of people wonder why is that pattern there? It's actually because of the very last digit in your barcode. All the other digits are the actual product code, and the last digit is added on afterwards just to make that pattern work. It's called a check digit. And because you have this check digit that completes the pattern, a checkout can double-check the patterns there when it scans a barcode, and it knows when the laser reader has misscanned a barcode. So this way, we catch most of the mistakes that would otherwise be entered when barcodes are misscanned at the checkout.
So this is effectively a way of making sure that the scan has occurred correctly by just reading one number, rather than having to read the whole lot again. You've actually got the whole thing in one number in order to check your work.
Yep, so it can check straight away because people get upset if it was just entering a number without checking if it's right or not. You might scan a packet of crisps and get charged for a big screen television, and people get very emotional about these things. Unless it's the other way around, I guess. But this way, the checkout knows if it's a real barcode number or if it's just a random misscanned number.
It's not just barcodes that this science applies to, though, does it? Because this same technology can be used to rebuild data that's missing from things. We famously, on The Naked Scientist, drilled a hole in a CD, and it still played beautifully because of this sort of redundancy. You can use the numbers in these check digits to work out what would have been there previously.
Yeah, CDs use I think it's the Reed-Solomon form of error correction. And so text messages do this, digital television does this. They all work pretty much like a Sudoku, where with a Sudoku, if you know the mathematical patterns in a grid of numbers, you can recreate all the missing numbers just using the patterns.
Matt Parker, thank you very much. Matt Parker, the stand-up mathematician and also the celebrity who's part of Festival of the Spoken Nerd. Well, let's stick with hard questions. Ginny.
Now we've got Hannah Critchlow, who's been drawing on the walls for our question of the week.
The Naked Scientist's Question of the Week, brought to you in association with the Houter Wisman Foundation, supporting science and education from Alpha to Omega.
This week we ask where our ancestors artistically expressed themselves.
Hello, I'm George Cotterelli from Wirral, and my question for the Naked Scientist is, was prehistoric art, like cave paintings, only done in caves, or is that the only place untouched enough for it to be preserved?
We turn to an expert.
I'm Diana O'Carroll, and I'm a PhD research student and naked scientist. I think that the sorts of art found in caves was almost certainly done out in the open as well. Unfortunately, we can't prove this, but we can look at how cave art does survive and what other things humans were up to at the time. So the kind of art the questioner is talking about tended to appear around the Upper Paleolithic era in Europe, which was from about 50 to 60,000 years ago. And these include drawings of bison or people, dots and silhouettes of hands, and even a few seemingly random scribbles, with some of the more famous examples found at places like El Castillo or Chauvet or Lascaux. Now, the problem with paintings is that often they can be washed away with rain, or they can be blown away by wind carrying tiny particles which abrade the surface of the rock. It's probably worth noting that there are one or two sites in Australia, more specifically there's Arnhem Land Plateau, where there are some very old open-air rock paintings that have survived, although they tend to be found in quite sheltered areas.
And other than wind and rain, are there other ways that caves help to protect prehistoric artwork?
Providing the rocks they're made out of aren't too acidic, they're actually great areas for preserving both organic and inorganic materials. So that includes the charcoal-based outlines and the pigments, which were usually made of earth minerals like red or yellow ochre. Now, caves tend to stay at the same temperature, they have constant humidity, and sometimes they contain limited amounts of oxygen, all of which creates a fairly stable environment in which to preserve whatever people have left behind. More importantly, caves tend to fill up or become blocked, meaning that people can't get inside them and destroy the art. My favourite example of this is the Grotte Cosquer, which is so tricky to access that several divers have actually died trying to navigate its underwater entrance. But its remoteness is exactly what kept the painting safe for thousands of years.
That was Diana O'Carroll from Cambridge with her favourite prehistoric artwork in Marseille, France. Evan A.U., Clifford K. and Sifram agree on the forum, adding with Diana that stone carving and sculpture are another form of human art. At Ayers Rock in Australia, petroglyphs exist. These are shallow carvings of abstract lines or animals and strange, unidentifiable creatures. These are thought to be around 40,000 years old, and they're found across other parts of Australia, Africa, Asia, the Americas, as well as in Europe, somehow managing to survive out in the open. Now, sticking with the beginnings of humankind as we know it, but switching from art to campfires, with a question just in.
Hello Naked Scientists, this is Sean from Surrey. On a recent family camping trip, we were baking potatoes and toasting a few marshmallows on a metal grid over the embers of a fire. Whilst drinking a beer, I thought, if I could get my fire hot enough, I would be able to melt the metal grid, although perhaps not at campfire temperatures. But if I did melt the metal, the potato would either burn away or turn into something which resembles a lump of coal. The potato would not melt like marshmallows do if left close to the heat for too long. I'm pretty sure that most things can exist as a solid, liquid or gas. So my question is, what would I have to do to melt my potato to a liquid like I can melt a marshmallow? And would this be possible to achieve outside my tent and with a beer?
Sean Mooney got in touch with that question. What do you think about that one? Let us know by posting on our Naked Scientists Facebook page. You can tweet at Naked Scientists, or you can email at chris@thenakedscientist.com, or you can join in the debate on our forum, which is at nakedscientists.com/forum.
That's Hannah Critchlow with our question of the week.
Thank you, Ginny. Well, that is it for this week. We've run out of time. Thank you for all of your questions, but do keep sending them in to chris@thenakedscientist.com. Please don't forget that we are running our listener survey at the moment. There's up for grabs Amazon vouchers worth 10 quid, or the equivalent in your local currency, for you to spend on whatever you like. You just have to fill in our survey and tell us what you think of our programme, what we're doing well, and what we could be doing better. To find it, you just go to nakedscientists.com/survey, but do hurry, because you have only until 12/12/12 to get your applications in. Next week, we're looking at wildlife conservation, but it's not pretty and not charismatic. They're not cuddly pandas, they're not regal lions or beautiful birds, because we're looking at the conservation of ugly, infectious, parasitic organisms. So join us next week as we champion the cause of protecting nature's less attractive animals and preserving parasites and microorganisms. Thank you to our production team, Hannah Critchlow, Tom Simpkins and Ben Vousler, and our special guest, Matt Parker. Until next time, goodbye.
The Naked Scientists podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the STFC, the Natural Environment Research Council and UK FAST. For more cutting-edge science, join us online at nakedscientists.com.